Hi, I'm Jesse Dillon. This is Jesse's Office. Today we're talking to particle physicist Edward Farhi. We're talking about quantum mechanics, CERN, black holes, artificial intelligence, what's behind everyday reality, the joys of inquisitiveness, how to weather the current anti-science climate, which is a big problem. First, please subscribe to our YouTube channel to watch this and more episodes, or subscribe to Jesse's Office wherever you stream your podcasts. Leave comments, reviews. I try to respond.
Hi, I'm Priscilla.
Priscilla?
Yeah, hi. Would you like some water?
Maybe I'll have some water with this, sure.
Yeah.
Some water, please.
Eddie, how are you?
Please.
Welcome.
Thank you so much.
How are you doing?
Fine. You can
good.
move that around if you want.
Yeah, I could.
How are you doing?
I'm good. Still working hard and, traveling back and forth.
Hopefully you're going to tell us a little bit about physics and the way that you think about things. But why do we want to understand physics? How did you even get started thinking about it?
Well, when I was a kid, I became sort of interested in things like atoms and, equations, but I didn't really understand them too well, obviously, because I was small. And then I just always got intrigued by the notion that there was a way to understand the world which went beyond your senses with a kind of...
Did you already, when you were young, did you already have a grasp of math?
My math skills were decent, but then I was lucky I went to the Bronx High School of Science.
And did they see you come in the door, say, because it's a very famous school. A lot of people attended this school.
Well, 8 Nobel Prizes in physics went to the Bronx High School of Science.
Wow.
Which is kind of astonishing for one high school. Anybody could go to the Bronx High School of Science who took the test and got in. And so it was fed by all of New York City. And so I met kids at the Bronx High School of Science who came from, I grew up in the Bronx, but kids from Manhattan and Queens and from far away. And I met kids who could have gone to any private school in the city because they were very affluent and their parents were powerful. But once they got into the Bronx High School of Science, they went there. So it was a magnet for kids who were interested in things.
And do you feel like that was formative in some way? Did you have a teacher there that...
I was, well, yes, in certain ways, but partly it's because I could talk math with the other kids. Mm-hmm. Like it was a place where you could be comfortable if you were interested in science or math. It wasn't so much the teachers they weren't better than the teachers in regular schools, but they let the kids be.
Right.
Because,
When you say talk math, like I'm not a good math student. I mean, I understand the beauty of it, that it should be taught next to English, next to composition, but I don't necessarily see the great mystery of it. Why is it so important in physics to understand math? Because we can't...
Well, that's an eternal question, which is, why is the world described mathematically successfully? There's no real answer to that. That's a mystery. The fact that, Mother Nature reveals herself through mathematical equations, which can be used to describe the world, is a mystery.
Right.
And people talk about, the unreasonable effectiveness of mathematics. And I think that I don't have an answer as to why mathematics is the language of nature. Right. I can't answer that.
Right.
But it's kind of a gift, I guess, from the heavens that we could somehow or another be given a tool, which is mathematics, to describe the world around us. But I don't know where that comes from.
When you said, though, you were thinking about atoms really early on, what was it? Like, you were interested in something, but were you in your head, or were you seeing things in the world? Like, what?
No, it was in my head. No. I mean, I also had a sense that this was a higher calling, that, if you could be good at this and pursue it, that it was kind of a noble path. I felt that.
Like, how old were you?
Maybe 12.
A lot of times people say, well, physics doesn't have an application in the real world, and yet it touches everything. So how do you like our cell phones work off of it. I mean, like
right. I mean, well, that physics. I mean, when you fly on a plane, it's not held up by prayer. I mean, it's held up because
it is in my case and my arms. I keep everything
you put your hands
moving.
out. Right.
She's terrible.
I mean, the world is described by physical law, and that's just the way it is. Now, when I talk about the physical world in a sense of physics, I'm talking about the world that can be described effectively mathematically. So I'm talking about where you look at things, you measure things like speed or weight or velocity or temperature or volume, so that, you can ascribe numbers to things. I'm not talking about, feelings or joy. I'm talking about the fact that you can ascribe numbers to things, like how high up is the plane? How fast is it going? What's its rate of descent? What's the thrust? What's the lift?
When we talk about a standard model,
Yes.
like why are we struggling? The scientific method is to always keep testing this, be engaged in this conversation. We never reach a state where we say, everything is one way. In your mind, how do you think about the scientific method?
Well, okay, so since you mentioned the standard model, that then we're going to have to talk. I think, let me talk about it in that context, not so generally, because that brings us to particle physics, which is where I was trained. I have a PhD in particle physics, and I worked at the National Laboratory, Stanford Linear Accelerator Center. I worked at CERN.
Right, so before you start, I just want to play this for you. This is the sound. This is the sound. That's the sound of the particles smashing into one another at CERN.
Is it really the sound?
That is really the sound. I mean, the question is, when you hear that, like, it's hard for me to understand. But at CERN, you go down into it, you look around, you look up at this experiment, and I think it costs $10 billion,
Something
and
like that.
you look at it, and it has no other purpose except to tell us something more about the universe than we knew before, which it successfully did. But how did you think about it, working on it?
As a particle physicist, I bought into the reductionist view that we could learn about the universe by going to smaller and smaller distances. And so when I entered, we already knew that atoms had a central core called the nucleus. The nucleus is made of neutrons and protons. The neutrons and protons are made of quarks. So I was studying properties of quarks and similar particles. And again, why it is that, that reductionist view that you could go smaller and keep learning, I don't know why that is. But particle physics did kind of hit a roadblock where we have a very good understanding of many things in particle physics, but there are many deep unanswered questions which have not been answered in the last 30 or 40 years.
Why did they call it the God particle? Like
the Higgs boson, the God
particle. But why would you call it? Why was it named that?
I think that was just like I think that was Leon Letterman, I think, who named it that. Yeah, I think that was just, a little excess maybe to sell his book. I don't know.
But the thing is this, is that we did realize that we did discover that there is a Higgs.
That's right. Look, when the Higgs boson, the standard model of elementary particle physics is a set of equations which describe the interactions of the quarks, there are 6 of them, and the leptons, those are the electron, the muon, and their partners, the neutrinos, and also the force carriers, the gluons and the photon. Anyway, in that model, it was shown that there should be another particle. This was actually written down, I think, in the form that we really bought into it by Steven Weinberg, who went to the Bronx High School of Science.
But now we
did
did find it. I don't think we don't, but we did find it.
I might.
But it wasn't exactly what it was predicted, and so
not exactly. They could never predict its exact mass.
Right.
And so the discovery nailed down its mass.
Right.
But its mass was within a range that it wasn't bizarre. In other words, had it been 100 times heavier or 100 times lighter, it would have been more controversial.
Right.
But so the discovery of the Higgs boson, which was an amazing experimental accomplishment, just confirmed belief. Like, it didn't change anything in my head because I knew they were going to find it, and then they did.
Right.
And so nothing changed for me other than an amazing and complex experiment was done.
You said earlier, okay, we wanted to find this thing, and we would know something. What do we know when we...
Well, we know that there is a set of equations called the standard model, which successfully describe the interaction of all the constituents of matter that we know about. Now, those equations are kind of complicated, and it reveals something about the world, that, there is a mathematical framework for describing elementary particles. It's just revelatory that you can write it down and look at it and understand it.
But like for people listening, is it that we're seeing nature in action?
Yes.
Is that what
it's seeing nature in action, but nature reveals herself in a kind of mysterious way because there are these equations that describe things, but the equations have properties. They're consistent with the theory of relativity and with quantum mechanics, and there's a whole framework for understanding them, which, you ask me to describe. I have some difficulty describing it because I don't really understand it. In a way, I just look at it.
If you don't understand it,
no, but can anybody understand it?
Well,
We
it
just
depends
can
on what we
see.
mean by understand,
We can see it. We can use it, but we don't.
Right.
We can't rebuild it.
Right, it is what it is, and we can have intuition about it. You can use it. I can understand it. I understand it well enough that if you asked me a specific math question about it, I could probably answer it. Like if you said to me, "Can you predict this?" I would probably know. Or is it consistent in this way? I would probably know. But in terms of a visceral understanding of the world, I'm not sure that I have that.
So Kip Thorne's experiment on gravity took 50 years. Do you remember where you were when you just saw the result of that, and how did that change Can you describe it and just what it means to have a
the discovery of gravity waves? Yes, I know where I was. I was at MIT because one of my colleagues, Ray Weiss, was one of the leaders of the experimental effort, and I was amazed by that. I couldn't sleep at night after the gravity wave detection because, that was, in my humble opinion, that was the biggest discovery in physics in 30 or 40 years, because not only did they discover gravity waves, which had been predicted by Einstein 100 years ago, which was a great confirmation of the theory, but they did it by building an exquisitely complex machine, which works at an almost unfathomable precision. They built it against all odds. People were betting against them, and yet they built it. And then, they got a little gift from Mother Nature, because what they saw on the first observation was the collision of two massive black holes 1 billion light years away.
Within 20 minutes of turning the machine on.
Yeah, turning the machine on. Mother Nature was kind to Ray and Kip for their diligence. And, suddenly, the thing was not just a confirmation of Einstein's theory, but it discovered a new phenomenon.
What was the mood like in the room when?
Well, it was just like everyone at MIT was just blissful. Like I was teaching quantum mechanics, and the next day I came in, I said, "We're not talking about quantum mechanics today. We're talking about gravity waves."
Right.
Because this is really a big deal.
And this will create a whole new field of study, yeah?
That's right. Mm-hmm. Because they didn't expect that they would see. They were expecting to see neutron star mergers where neutron stars have like a solar mass, and they whip around each other and they fall in. But they found 30 solar mass objects, and they were much further away than they thought they could ever pick up. And that's because they were more massive, so the signal was bigger, so you could pick it up even though it was further out.
We've been looking at physics since maybe Newton, right?
Yeah,
So
yeah.
it's like, how do you feel about time relative to physics, and how we as a small group of brains can really build this standard model? And if we do build it, are we going to build it quick enough that we can actually do anything about it?
The fact that we have managed in the last 1,000 years or so to write down a very successful mathematical theory of the world, and it's been accelerating. Newton was, one of the, in my opinion, one of the greatest intellects who ever lived, because he realized that you could have a mathematical description of the universe, and then he wrote down the universal law of gravity, and he invented the calculus, and he solved it.
But he put it in a drawer, didn't look at it for 20 years.
Well, he had other interests, which was kind of fascinating about Newton. I'm not really a great student of history, but Newton's law of gravity, it was only modified by Einstein. And in my opinion, Einstein's general theory of relativity, which I have taught, and I have written papers on. So I feel like I have a pretty good understanding of it. I think is the most beautiful human creation of ever.
Right.
Why?
Because it was so radical. I mean, it's not just that Einstein was incredibly talented mathematically, but he adopted radical notions, which then turned out to be true. Like, well, the first thing he did was before general relativity, he did what's called special relativity, and he showed that, time is not this immovable thing measured the same by everyone, but the amount of time that elapses between events can depend on the velocity of the observer. And that means that, if you go up in a rocket fast enough, you can come back to the Earth having aged less than your twin. And, to realize that, and to, just throw out the notion that time was a constant for all observers, and then to show mathematically how to do it, and then...
Time travel's not possible, though, in your mind.
Well, there's very good reason to believe time travel is not... Time travel means going back in time.
Right.
You can skip into the future.
Right.
Right.
Like I could send you on a path now, and you could come back to the Earth, and let's say 1,000 years have gone by, but according to you, only 10 or 20 years have gone, or 1 year has gone by. So you greet your great-great-great-great-grandchildren, but there's no going back.
Wait a
in the because you can go forward in time, but you can't go backwards. We're all
so you're
sense
just there
time
and then
traveling.
you stay there.
Well,
Once you arrive in
Yeah.
the future, you cannot come back.
But
You can skip into...
I hate to break it to you, but yeah, you can't go back.
Yeah,
no, I
you can't
understand.
go
I
back.
might be in the future right now.
Well,
we
you
are
are.
presently
We're
marching
moving
into the
into
future.
it as we move along.
Yeah, we are. We're heading into the future at the second, but you can skip ahead.
This is also demonstrated by when we send signals off of satellites because they're slightly in different positions, so it's only microseconds. But if we didn't know about that, if we didn't have Einstein's theory of relativity, we couldn't actually do that.
Because when you do GPS, you're communicating with satellites which are circling the Earth, and I think they're going like 25,000 miles an hour, something like that.
Right.
But that's enough that there's a tiny relativistic effect, which means that their clocks are running at different rates. And if you didn't take that into account, then you would be driving, 40, 50 feet to the left of where you think you are.
Now, do you remember where you were when you saw the photograph of the black hole?
That I saw in the New York Times only. I think I just saw that in a coffee shop in Venice. That one I haven't wrapped my head around that. I have to say, it's been a little bit, I haven't actually wrapped my head around it.
If you were to wrap your head around it, because you guys are, your head, my head can't even wrap around this conversation, honestly.
Yeah.
What does a black hole mean? What is it?
So, Einstein wrote down this theory called general relativity, which is the apparently correct theory of gravity. And if you solve the equations of general relativity for what the gravitational field looks like outside of an object, you discover that if the object is compact, and there's a definite sense of what that means. It means that for an object, let's say like the sun, it would have to be actually smaller than a few kilometers. So if you compress the sun down to a few kilometers, there's a thing called the Schwarzschild radius. It doesn't matter, it's a technical term. But the sun, I think the Schwarzschild radius of the sun is 6 kilometers. Maybe I'm wrong, but it's about that. And so if you compress the sun smaller than that, the sun would be a black hole. And that means that there's a certain distance from the center of the sun, which is called the horizon. And if you are inside the horizon, closer to the center than you are at it, then you cannot get past the horizon by any means. There's no matter how powerful your rocket is, you cannot get out. And also, if you shine a light ray out from inside the horizon, it will not escape the horizon. It'll get frozen at the horizon.
I've met a lot of people like this.
Yeah, there are a lot of people like that on those properties, yeah. And it's just this place where if you cross the horizon, if you fall in, you just never come out. And so it's the ultimate doom.
But, is that real?
Yes.
It's
Yeah.
real. So,
Because they've seen that there are 30 solar mass black holes.
But
They
who's
just
in
saw
there?
the collision of two of them.
are objects in there, stars are in there, things are in there, universes, right? We don't know.
You can't see because it's all
You can't
goes
see what's
in.
on the other side, right?
Yeah, it all
Right.
disappears.
You can't really know what's on the other side of the black hole because you can't go in there and come out and tell anybody. But now there is good evidence that there are black holes out there in the universe.
So
There are none in this room.
Yeah. When you're going to do science, when you're going to think about a question,
Yeah.
who do you do that with? And is that 10,000 other scientists getting together in a room, or is it you and a couple of friends in a coffee shop?
That's a good question. Today, for example, I had a video conference with two of my collaborators, one of whom I met at the Bronx High School of Science.
Right.
And his name is Sam, and we videoed. He was in Boston.
And how long have you guys been collaborating?
30 years.
And so when you want to think about science in a different way, how important is it that you have these close relationships and that you work together?
I need to talk. Yeah, I'm a talker. I like to talk to people. I like to share my thoughts. I like to, but first of all, if you talk to people and you share your thoughts, you save a lot of time.
Right.
Because you can easily be saying, and Sam and my other collaborator, Jeffrey, who I was also talking to today, they'll just shut me down if I say something which is not right, and I'm grateful.
Right.
Because, I don't want to waste my time.
But what would be an example of an idea that you might talk about?
Usually it's technical mathematical stuff. I might think that, there's a relationship between two mathematical objects, which must be true, and then I'll talk to them, and they'll say it can't be because I'll give you an example where it isn't true.
Right.
Something like that. So that's the end of my little idea.
And is that how we create scientists, groups of people getting together in rooms and
Well, I can't. Well, yes and no. I mean, Einstein was obviously a loner,
right?
But I don't think you can ever use Einstein as a paradigm for anyone's personal behavior,
right?
Because he's so extraordinary, you know. Or Newton, it's ridiculous,
right?
It's like saying, I want to be a musician, so I think I'll go see what Mozart did,
right?
Good luck,
right? Right.
That's
and
just
also
too extreme.
Science was smaller then, so he had these discoveries at a point. Now it's become so specific. It's like you're looking at individual aspects of ideas.
Yeah, it's harder.
Yeah,
it's harder because the more we know, the more specialized your knowledge. And there's high school kids are not making contributions to theoretical physics. It's impossible. It's not because they can't know enough.
When you teach, what do you recognize? Is there some thing in a student where you go, wow, this one's really going to be something?
I can tell from the questions.
Really?
Yeah. Particularly if you I can often tell by the nature of the question. If the question is, can you repeat what you said?
Right.
Okay. Or can you explain again why the left-hand
You mean the
side...
things I'm asking.
Right. Can you explain again why the left-hand side of the equation is the right-hand side? Sure.
Right.
I mean, I'm happy to do that. Maybe a good student.
Right.
But sometimes you get a student who says, in the beginning of the lecture, you said this. And at the end of the lecture, you said that. And those contradict each other.
Right.
Why'd you say that, Professor Farhi?
And what do you do?
Well, then I'm like, oh, yeah, good. Let me try to resolve the conflict between
first of all, were they right and you were made a mistake?
They're right. They're right. They pointed out a contradiction in something I said. So, yeah, of course, if that kid is a great student who sees that I said something, contradicted later in the lecture, and therefore I have to go back and clarify and think, why did I do that? Yeah. So if you have a student who does that, you're very happy.
We were together at a conference on quantum computers.
Yes.
Now, what do you think is, a lot of people think quantum computer is just a faster computer. Is that what a quantum computer is?
No.
Because you kind of work on this at Google on quantum computers.
I do, yeah. So let me just think for a second, yeah. So about 20 years ago, I was doing particle physics, but then I shifted my interest to quantum computing. We could talk about that if you want to know.
What moved you from
we do want to know.
From physics to
from particle physics? Yeah. Well, it was two things. One, I was becoming frustrated by particle physics because I was having trouble making progress.
Right.
Particle physics is really hard.
Yeah.
Right.
And it's really hard to make real progress.
Whereas quantum computers are really easy.
No, but it was new.
Right.
No, it's uncharted.
Right.
No, it wasn't obviously, but particle physics I'd been in for a while, and I could see that the questions were really tough, and I felt that the community wasn't making progress.
Right.
And people were becoming sort of ideological in their belief systems, which a lot
Right.
of which I didn't believe.
Right.
And I was sort of unimpressed with the kind of common belief system of particle physics,
Yeah.
which in retrospect, I feel I was right about because a lot of those beliefs didn't work out.
Right.
But that's not the point. The point is I felt an unease, and then I read a paper that showed that if you had a quantum computer, it could solve a math problem that could. What I mean by solve is this. Maybe we should be clear. You see, computers solve. I'm not thinking of a computer as a device to search the internet. I'm thinking of the computer as a device to solve a math problem.
Right.
Or a certain type of problem. And the one question you can ask is, how many steps does the computer take to solve the problem?
Right.
Now, if you ask in terms of the number of steps, it doesn't matter whether your computer is an abacus or it's a digital computer made with the fastest components, because if you're worried about the number of steps, the individual mechanism for executing those steps is not the concern of the person designing what we call the algorithm, the
Right.
process for getting the answer. It's the steps. And so what was shown is that if you had a quantum computer, the number of steps required to solve a certain math problem was way fewer than the number that seemed to be required by ordinary computers.
Why would we need a faster
Yeah.
computer?
Well, that particular problem, if we go back to that one, which was called factoring. I mean, I can even tell you what it is. Let's see if we can understand this. If you have a number like 33, you can write it as 3 times 11, which is the product of 2 primes. Primes are numbers which only are divisible by themselves in 1.
Sure.
You know,
We both know that, right?
we know that, right? So now, if I give you a little bit bigger number, I did 33. Maybe that's the biggest one I know. I don't know. There are bigger numbers at which we could factor, but you could ask a different question, which is not really one of the factors, but how would I go about getting my computer to find the factors?
Right.
So that's the algorithm question.
Right.
How do I program my computer to find the factors? Well, it turns out that conventional computers are not that good at factoring big numbers. And what I mean by a big number is a number with 1,000 digits.
Right.
But 1,000 digits is very easy to write down. Just 1,000 digits doesn't take you very long to type out. And computers, the number of steps required to factor a 1,000-digit number is so enormous that ordinary computers cannot factor them. But the quantum computer was shown, if you had a big one, could factor very quickly.
Now, why, beyond security, would
Yeah.
it be important that we have this
Well,
computing
you
power?
brought up a good point, which maybe we should share, which has to do with the fact that the inability to factor large numbers is a basis of encryption systems used by the bank and the military. So if you had a machine that could quickly factor, you would break existing codes. So that meant that this particular algorithm had a kind of killer app,
Right.
which is breaking codes.
Right.
But that's a separate question from its intellectual interest. But
Right.
of course, it was important to the development of the field.
Sure.
And it's why the government got very interested. But aside from that, what fascinated me was the math question, which is, why is it that a quantum machine could how can quantum mechanics take advantage of the structure of factoring to allow it to factor more quickly? So I saw it as a really interesting intellectual challenge.
And if we were able to do that, like if we're able to build these computers,
Yeah.
which are different because
Yes.
they're not just faster, they
Right.
have a different thought process,
Right.
if that's the right thing to say.
Yes.
Can we even predict what we might learn from them? Or
No, I don't think so. After I saw the factoring algorithm, it was already done, So then I started asking whether there weren't other things one might try to do. And I have been interested in applications of quantum computers to other problems. And I have been searching for problems where quantum computers might be of value. And I have some success in that. But I am very open to the possibility of just building a quantum computer, running it, and seeing what we can do with it.
What would be other areas that would be beneficial?
Okay, great question. Well, one thing you might use a quantum computer for is to help you do simulations of physical systems which are themselves quantum mechanical. So, for example, suppose that I want to model a complicated atomic system or molecule or chemical process or material which is described by quantum mechanics. So you might attempt to do that with a conventional computer. But Richard Feynman was the one who said, if you want to model a physical system whose underlying structure is quantum mechanical, you're best off using a quantum computer. So there's a lot of interest in using quantum computers for chemistry problems, simulation of materials. That's not what I work on, but that's a big area.
Will it change the world? I mean, will
It could. I don't know. I can't. I'm not going to make predictions, especially as about the future. But
You're not?
Because we're not there yet.
no, right.
Well,
But
Is it possible we're in a simulation now?
I don't know. Sure, I guess.
Yeah.
I guess. I mean, I don't have free will. I know that.
People have talked about using artificial intelligence with quantum computers.
Yes, they are.
Now, every time we hear about that, we hear about it in a dystopian of framework. But
Yes. Well, one of the steps to artificial intelligence is something called machine learning, where machines learn. And I have been interested in the question whether quantum computers could learn different types of things than ordinary computers. But I don't see, clearly a path forward for using quantum computers to machine learn in a way. But it's interesting.
but did they just announce they're going to have their commercial one?
Well, yes, IBM has built a big box, which has a very nice look, and they claim that inside of it is a quantum computer. And
although it's like machine learning, we can define that a million different ways what it is, right? Is there a definitive quantum computer?
well, it's small. I mean, the thing is that ordinary computers, an ordinary computer, you can think of it as made of logical components, which are bits. Bit is a 0 or 1, or up, down, or left or right on the abacus, or something like that. And the basic building block of a quantum computer is called a qubit, Q-U-B-I-T. And, so people are struggling to build quantum computers. And obviously, the more qubits, the better. But it also has to work well, because if you have a big box of crappy qubits, doesn't help you either. So they have to be, we have a technical term for it, high fidelity, meaning that they work well, qubits. And IBM has built a very tiny 20-qubit quantum computer with a certain fidelity that is not going to allow anyone to solve a math problem they couldn't solve without it. But they're taking steps.
Right.
And where I work at Google, similarly, they're going to one day announce a bigger quantum computer than 20 qubits. And it will not be something that you could take and solve math problems that you couldn't solve with a conventional computer. Don't forget the competition is fierce. Conventional computers work really well.
Yeah.
And so, we're just at the beginning, taking baby steps in quantum computing, building tiny ones.
If we build a quantum computer, physically, what does it look like? Is it a coffee table? Is it a big room? Is it is there a control room? Like, how do you think about it?
Well, I personally am not a hardware guy. I'm not trying to build the device.
Right.
I'm just I'm trying to figure out what to do with it.
Right.
And so to me, to some degree, just who I am, the actual details of how the device works is less important to me than, let's say, what its power is. It's kind of like, like if you drive a car, and even if you're racing a car, you don't necessarily need to know everything about the internal working to still have some sense of how to deal what you want its performance to be. So I am not a hardware person.
Right.
But I would say the following, that there are different platforms which have been proposed. And Google is trying to build something with what are called superconducting qubits. Right. And in this technology, the experimentalists actually manufacture the qubit. They do it by building a little, what's called superconducting circuit, which is a little tiny little circuit in which current is flowing one way, that's
Right.
a 0, and current flowing the other way is 1. In order to get the device to work, it has to be very cold. So it sits at a millikelvin, which is a 20 millikelvin, I think, which is, a fraction of a degree absolute, which is very cold by ordinary standards, but it's not super cold by the standards.
But like
of
how
physics.
cold? Like 50 below zero? Like how?
No, this is 50 below 0. No. This is, if you went to absolute 0, this is like a 100th of a degree above absolute 0. That's really cold.
That's cold.
But people have gone to nano Kelvin, which is 10 to the minus 9 degrees above absolute
Right.
0. So we're talking really cold. So anyway, at the Google device is made with superconducting qubits, as is the IBM device.
Right.
And then what's hard to do is make the qubit, and then you have to control them, because it's never enough to have isolated qubits.
Right.
Because you can imagine, if you want to add numbers, you better be able to take 2 different bits and add them. Otherwise, you don't have any
It's
power.
a bit without
Right.
another bit. I mean,
Yeah, you have
two
to
bit.
connect them. So there are issues, which is how good are your qubits, how good is the operation between qubits, how long does it maintain its quantumness. So the superconducting technology is the route that IBM is going on, and so is Google. But there are other technologies. There are people who instead use for the qubits atoms. Now, the advantage of using an atom is that it's already a perfect qubit, because you didn't make it, and
Right.
all atoms are the
Right.
same.
Right.
And they all have the same wonderful characteristics. And so people try to put atoms into what are called optical traps. And they do this with charged atoms, neutral atoms. And here, the atoms themselves are perfect qubits, but the control is more difficult. So I would say the world has not settled on an absolute path forward for the hardware.
Although that's pretty natural for where we are now, because we have no idea what the standard will be or why the standard
Right.
should be.
Or even why? Like, why does Google want to pursue this, right? Because we don't even know. You're saying maybe we don't even know what the application is yet.
Well, the application for them would be they have lots of computers that they need to make rapid calculations. So
that's all. It's just to be better at their. So it's a business model.
Ultimately, I imagine
Right?
it's a latency issue. The faster that you can do the calculations, the faster it can be. The more data you can push through it, the more as we have an interconnected world, the more stuff can be thrown at it. Yeah.
Yeah, well, I think that's part of it. They would like to use quantum computers as integrated into their regular conventional computer system. So you would have hybrid computers, which have both quantum and what we call classical. Classical means non-quantum.
A lot of times, we don't know what these applications or things could be. Is that the interesting part to you?
Well, I have to say that, I'm very comfortable with the uncertainty of not knowing what I'm going to be doing in a year in terms of my own intellectual interest.
Right.
I am a little less guided in my research than one might imagine.
Right.
I just kind of wander. And, I'll be interested in whatever I'm doing in a year or tomorrow, but it's very hard for me to predict what that might be, or I'm not so guided by a principle that says I have to go and do this. I don't have vision in that way. I make small incremental advances which accumulate.
But this group that you're part of at Google collects people like you who
Yes.
are working at this very high level
Right.
of something else and brings them
Right.
together in the idea that something special could happen.
Right.
What's that process like? Without,
Well, basically at Google, we all sit in one big office, which is rather different than in academia where...
So it's open? Is it an open office?
Yes.
Yeah.
Yes, anyone can walk in. And so no one has private offices.
Now, were these all people you knew before? Because these are all people with the same sort of level of pedigree.
Not every single one, but it's not that big a community. I'd been to enough conferences and spoken at enough meetings that I was roughly familiar with the people who work there. There are different people in the office with different needs. Like some people are really focused on trying to help the hardware team build their device. And so that's a very specific and useful task. I am on the speculative end. I try to imagine what a perfectly functioning quantum computer would do.
Right.
And I try to develop algorithms. But Google is kind enough to allow me to continue my collaborations with my MIT buddies. And I travel often to MIT to continue those collaborations.
Do you find new collaborators here in Santa Monica?
A little bit, yeah. Yeah, I have found some new ones. But I have, and in the fall, I worked with an intern who was he was a PhD candidate, and he came to me and he said, Eddie, I just discovered this little thing running something that's related to your work. And I said, really? And he said, yes. And he told me something I didn't know. And, I'm very happy if a kid comes to me and tells me something I didn't know.
Or that you made a mistake. We remember that, too.
Yeah,
I mean,
right.
You've been at MIT for how long?
Well, I was at MIT. I became a professor at MIT in 1981.
So what's it been like moving to Santa Monica for part of the
Well,
year?
it's different. I get to ride my bike on the beach and, enjoy going to the Gold's Gym.
I live in Santa Monica. Which gym do you go to?
Gold's Gym.
Of course.
I go to Gold's Gym in Venice,
So whatever your workout thing, are you still thinking about these? Like, do these ideas still consume you?
Well,
are you counting?
Sometimes, I can be on 24 hours a day. In other words, I wake up, very often I wake up in the middle of the night and I work in my head. I don't get out of bed.
You don't write anything down?
No, I just keep it in my head.
And how do you remember it when you wake
I
up?
could just remember it when I get up.
You need to tell me how to do that.
Have you found collaborators at Gold's Gym?
No. But once I was wearing my MIT shorts, and one of the trainers came up to me and said, we consider Gold's Gym to be the MIT of fitness.
Oh, my God.
Well, Priscilla definitely considers that.
No, I agree.
Yeah.
I said that. I was very flattered by that.
You see people really working on their body.
Yes.
And it's insane.
Well, it's the same way as they're working on the standard model of the universe, except they're working on their bicep.
But I want to ask you a question about, you're really interested in solving mathematical equations or there's numbers, but do you think about colleagues that are biologists or chemists? Do you feel like they're alien, or do you have some kinship with?
Well, that's a great question. I mean, one of my closest friends is a neuroscientist, and we talk about things. I think I feel kinship with anyone in science because I think science is a higher calling, and I think it's I'm not afraid to say that or embarrassed. I think it is a higher calling, and I think it's I feel extremely lucky to be a scientist. I feel like I won the lottery by being a scientist.
And even though there's all these specialties, isn't, Feynman, I think, would say, he has that beautiful description of a bird, the bird, you can describe all the things about the bird and still know nothing about the bird. And it's like, in a way, you can, whether you're entomologist or you're a particle physicist, we're all just trying to, well, no, we're not.
Right.
You're all trying to describe the natural world in its.
Well, that's right. I mean, but on the other hand, suppose you look up at the sky and you look at the stars at night and you think they're really gorgeous and stuff. But then suppose I told you that, I know something about the stars. I know what, the process that keeps it burning. I know why it has the color it has. I know how big it is. I know how long it will live, given how big it is today and what color it is. I think those things just help you appreciate the beauty of it. In other words, that knowledge of the details of things doesn't detract at all from a sense of wonder or beauty. And I think certainly when it comes to the cosmos, the fact that you can look out in the sky and know something about it is, I think it just adds to your sense of wonder and beauty.
Is there any literature that you've read that really describes things in the way, or is there a poet that you feel can take things? Do you ever connect with?
Yeah, I'll be honest with you.
You don't read?
I do read, but I tend to read like Philip Roth and things. I tend to read
that's interesting.
Yeah.
Oh, you like drama.
Yeah.
I'd rather read drama than I would read. I tend to not read like science stuff when I'm reading. I'm more interested in stories.
So, okay, so within science, there's an idea that the one thing that I think people don't get about the scientific method is that it like we can look out and see the stars, and 4 billion years from now, we know that all of atoms are moving apart from every other atom into this, but we don't know whether we end in, every inky black darkness, or if everything's going to come back together.
We don't at the
big
end?
crunch.
Well, we don't know. Well, we don't even know if there is an end, because maybe there was a time before the Big Bang. We just have no idea. So science doesn't solve every mystery. It's still just as beautiful and wondrous as it could ever be. So how do you think about that?
Well, I just think it enriches my life in the same way that music does, or, going for a walk in nature, or looking at the sky, or eating a good meal does. It just enriches my life, but it does not answer fundamental questions about, like, what's the meaning of life, or
Well, I
why
thought
am
you were
I
going to
here?
tell us when you came in here.
I was going to tell you, but I don't know.
So you still have those same questions.
Sure, I do. Although, I think science does make you realize sometimes, though, that, certain answers are probably not acceptable. Like if you believe that, there's some force that's very beyond science that controls things on the earth or something, you become very suspicious of things like that because there's no evidence for it. And you also find that a lot of times those explanations are not as interesting as the scientific explanations. Like, the story of Adam and Eve is not as interesting as the theory of evolution. It just isn't. Yeah. And it's also not true. And the theory of evolution is. Yeah. So, you're better off, I think, with that. Yeah. And there are many examples of that where the scientific explanation trumps the religious explanation or the mystical explanation. It doesn't mean that you can't be mystical or enjoy things, but if you're looking to explain the world with those things, I think when you're a scientist, you become pretty skeptical, especially when you see the success of science and how well it does in describing the world. And also the novelty, right? I mean, the novelty of evolution compared to creation myths is so astonishing. There is no creator. It evolved. Well, everyone thinks it's here, therefore there had to be a creator. It's here, there had to be a creator. Darwin said, no, it just could have evolved.
Right.
Why do you think we're in such at least here, such an anti-science era?
I can't really judge that. I try to live in my own little world where I occasionally, in fact, I had lunch with Jesse, and he encouraged me to ignore the news.
Well, I encourage you to do that,
Well,
too.
I know, but I don't listen to Jesse about anything.
And I actually did, I listened to you a little bit. You said it's like, focus on the success of, the minority of individuals alive who enrich the world. That's what you told me.
Is that what you said? You said it.
And
like that?
I decided to
He says it more eloquently than
That was
I do.
well said.
Yeah. And so I decided to pay a little attention to that. So, I can't account for the current, situation. I don't know. It's way beyond.
There's no mathematical law of nature about pendulum swinging and all that.
No,
Okay.
I don't know about that.
All right. Well, we'll leave that for another guest.
Yeah.
I need someone to tell me
Yeah.
how we got
Well,
here.
thank you for coming in.
Thank you
It was
so
fun.
much.
I hope it was okay.
It was great.
fun.
Yeah, it was really
was
good.
fun.
Yeah.
Thank you.
Yeah.
It was enjoyable.
Wonderful. Yeah. Thanks for watching and listening. Don't forget to subscribe and click here for the next episode.